Alright, again, good evening everybody. So as we said last time, today I would like to use this lecture to go over a little bit of questions that you may have about what we have seen during this semester. Before that one, just a reminder that the midterm will be midterm number 2, so will be next Monday, so which is April 28th. And of course that will be through Canvas, like the first one that we did. We can do the same time that we did last time. Last time we did between 7:30 and 8:50. Is that right? So you will have the same time that we would have during class time, plus 5 more minutes to make sure that you can scan and then submit. So please make sure that you submit, think about these 5 minutes, because after that the assignment will be closed and no further submissions will be accepted either through Canvas, through email, and yeah, anything like that. I'm planning, I'm almost done with the structure of the midterm. So I'm planning to include several multiple choice questions, maybe around 10 multiple choice questions. Then I will put probably a couple of open answer questions. So you will need to describe something, explain something with these open answer questions. And then I will put one problem. So again, I didn't finalize 100%, but I'm pretty sure that this will be the structure of the second midterm. As I said, I don't yet. I didn't do this yet up to this part. I will also include the rubric. Once I'm done with finalizing all the questions. Yeah, because I don't know the exact number yet, to be honest. So, yeah, I don't know yet. So I was saying that so the problem will be a little bit more towards what we did in the second part of the semester, and the multiple choice questions and the open answer questions will be more comprehensive, so they can include things that we did from day 1 until 2 days ago. Make sense? And make sure that always 10% will be given to neatness and organization. Make sure that you submit neat work, organized, you explain the steps, and this will be for the 10 points of neatness and organization. I don't think there is anything else I need to mention at this point. So I guess we can start with questions about this. Is there any question about the second midterm? No questions about the second midterm. So it means that everybody is ready now, right? Sorry, say again. Well, yeah, I mentioned that the problem will be focused a little bit more on what we did during the second part of the semester. The questions, so the multiple choice questions and the open answer questions will be more comprehensive, so they can include the topics that we did from day 1 until 2 days ago. Well, yes, but you need to know also what we did in the first part of the semester. You know, to solve two degree of freedom problems, you also need to know how to, you know, solve one degree of freedom problems. So that's why I'm saying it is a little bit more towards what we did in the second semester, but still, you know, covers what we did during the entire semester. Other questions? I don't think that will be needed, to be honest. Because, yeah, for the problem I will ask to show all the steps. If you use MATLAB or any other, you know, software, it means that the software will do the steps and you will not be able to show them, which means that you will lose points. But very good question. Thank you for asking. Go ahead. Oh yeah. We can use this time. I didn't prepare anything. Last time I said that you know, you can send me some email with your questions, so we can discuss questions, you know, during this time. But I didn't receive any email with questions, so I assume that you know, kept all the questions, you know, to ask them live and you know, find me as unprepared as possible, I guess. So if you have questions about anything that we did during the semester, we can start the discussion now. If there is something that you want to, you know, quickly review, or, you know, something that you need some clarification on, we can use this time for this. Homework 6. Okay, I need to look at it because I don't remember. Just give me a sec. You said homework 6? Okay, just one moment, please. Okay. So regarding the signs of this, you know, this type of problems, you need to set a certain coordinate system, and then, you know, when you look at this, you have to look at the sign of the forces. In this case, you would look at sign of moments. So, for example, if you remember when we were looking at the example with the two masses and the two springs, so when we have wall, spring, mass, spring, and then the other mass, so you would set your coordinate system with, let's say, positive in one direction, and sorry, so you have, again, positive in one direction, and then you would assume a certain displacement that is positive in that same direction, because you want to see what happens when you stretch the spring. So when you stretch, for example, the spring, or when you compress the spring, you will have, you know, a certain force in one direction. Let's use the paper so it's easier for me to explain. Just give me a second so I can share the screen. Where is share screen? So for example, if we look at so if you look at this example here, where we have M1, M2, and then we have K1 and K2, right? So if your positive direction for X is this one, you can assume this place, because since we are doing dynamic analysis, if we keep everything at 0 position, nothing happens, because if everything is at 0 position, it means that the two springs don't bring any force at all, because they are not stretched or compressed. So what do we need to do? We need to bring some that will, will have as a consequence the force from the spring. So for example, if this is your x1 and this is your x2, so if you assume that when we look at the free body diagram, if you assume that you have, let's say, a positive displacement for x1, for the mass number 1, you have that your spring is stretched, right? So if the spring is stretched, it means that it has it applies the force towards left. So in your free body diagram, for mass number 1, you will have one force that is in this direction, which will be Fk1, and then if you have a displacement in this direction, assuming 0 displacement for this mass x2, you have that K2 is compressed, right? Because if this doesn't move and this moves in the positive direction, it means that this one is compressed. So if it is compressed, it means that it reacts, it wants to extend, so the force that the spring applies on the mass would be also in this direction. So this will be Fk2. Right. And this is what's going on for the first mass. The second mass, same thing. So for the second mass, you assume a certain displacement on that specific mass. So assume that you have a positive displacement. At the same time, for the mass M1, the displacement will be 0 when you look at the displacement of mass 2. So if your mass M2 will move in the positive direction, it means that you are stretching the spring. If you stretch the spring, it means that the spring wants to pull back, so it means that your force from the spring number 2 will be the same, Fk2 in this case. So of course these are, in this case we have two forces, in this case we have only one. And when you write the equilibrium, the equilibrium equation, you would include both forces for this and only one force plus the inertia force, which is mass times acceleration. And of course your mass times acceleration, you have to give the positive sign, because you assume that you have a positive displacement, which means positive velocity and positive displacement, acceleration. Now if you look at the rotation for that problem number 3, the concept is exactly the same. So you will have a certain initial equilibrium condition, but if everything is in equilibrium, nothing is going on, because if you don't have any torsion on the discs, it means that the rods don't apply any force to react to that rotation. So you assume that you have a positive rotation for one disc while the other one is not moving, so that you can calculate your force back from the rod, and then do the same thing with the other one. So you assume that that one is going to have a positive small displacement while the other one is not moving, so that you can calculate the reaction from the two springs if there are two springs, or from only one spring if there is only one spring. So this case of this problem is actually very similar to this one. So the type of equation that you should obtain, except the symbols, because here we look at x, in that case we will look at theta, will be pretty much the same. Make sense? So it's the only difference is that here the displacement is a linear displacement, and of course the acceleration is a linear acceleration. For the problem number 3, you have rotational displacement and of course rotational acceleration. Make sense? Other questions? Yeah. Okay, let me look at the problem. Problem 7. So you ask about so we have number 7. Okay. Well, for the orthogonality, I mean, this is something that we can recall from linear algebra. What you need to look is is the product between the transpose of the vector and the vector itself. In order to have them not orthogonal, should be different from 0. Basically what you are doing is the dot product between the two vectors. So if the dot product between two vectors is 0, it means the two vectors are orthogonal, like perpendicular. So this is a kind of combination between geometry and linear algebra, basically. So this is the condition for orthogonality. Not to be honest, not super relevant for our problem. It's more for vibration application. It's more application of like mathematical, linear algebra mostly. Makes sense? Yeah, that's why I needed like a couple of seconds to recall this condition. Yeah. In this problem here. Okay, let's review it together. So here, when I'm talking about M1, let's see. So if we are moving the mass M1 in this direction, it means that we are stretching this spring, right? If we stretch the spring wants to go back to the original position, which means it's trying to pull the mass in this direction. When you look, so when you move this one and this doesn't move, so this is like at the 0 position, you are squishing this spring. So if you squish the spring tends to push you back. So this is the direction of Fk2. So this is the force that this spring applies on mass M1. Then if we look at mass M2, when M1 doesn't move and M1 moves in the positive direction, we have that we stretch this spring, which means that the spring tends to bring back bring back the mass. So we have the force that is Fk2 in this direction. So of course this is the case limit where we assume that there is no motion for mass x2 when we have motion on mass x1, and we assume that here we have motion on mass m2 and no motion on mass x1. However, keep in mind that when we were looking at at this problem for the first time, of course there can be motion on both masses, which means that what we have to look at is for this spring here is the difference between the two, the difference of displacement between the two masses. So this was like the case limit to understand where we have to put and how the two springs act on each mass. But if we go back to where we introduced this concept, let me see if I should find it. I think we looked at exactly this problem here. So in this case, what we have, sorry, it's a little blurry. Let me adjust. Okay. So in this is the case. This is like the when we analyze this one, this was like the most general case where we can have motion for both masses when we look at the free body diagram. So in this case, if we have a positive motion for mass m1, it's pretty much the same thing, because on this side we only have mass, we have only spring k1 that acts on the mass. When we look at the other side, again in the most general case, if we look at the motion of both masses, in order to determine the force of this spring over this mass, we need to look at the difference between the two displacements. Because if we look at the case that we had before, where we assume that we have no motion for mass m1, so x1 would be 0, and then we go back to the condition k2 x2, exactly like we had before. In this case, same thing. If you assume that the mass x1 is not moving, you will have k2 x2. Excuse me, k2. This is k2. So if we have positive motion of m2 and zero motion of m1, in this case, x1 will go to 0, so we have k2 x2. I call that fk2 in that case. Other questions? Yeah. So once you have the equations of motion, to find the frequency, you have to write the equations in a matrix form. Which means that you have to introduce the mass matrix and the stiffness matrix. So once you have the mass matrix and the stiffness matrix, you have to solve that. Just give me a second. Let me take those notes. I think I have notes somewhere. So basically you have to go through these steps here. Once you have the equation, excuse me here, in this case we had the equations, these are the two equations of motion, of course 2 degrees of freedom, which means two equilibrium equations. You write them in a matrix form. So here you have the mass matrix, acceleration vector, stiffness matrix, displacement vector. So once you come up with these two matrices, then in order to find the natural frequencies, you have to solve this equation here. You already have M, which is the mass matrix, you have K, which is the stiffness matrix. So once you have mass and stiffness matrix, you can build this equation here. So it is determinant of negative omega squared. In this case, omega is your unknown. So you multiply omega squared by the mass matrix, m1, m2, and then plus k. This is, 2 by 2. You just multiply these two terms by omega squared, and then you add this k1 plus k2. So this term will be the summation of this one as this one, this term, and so on. So once you come up with this 2 by 2 matrix, then you have to find the determinant of this 2 by 2 matrix, which means the product between this quantity and this quantity minus the product between this quantity and this quantity, which is what we have here. So we have this times this minus this times this. So, and then from here we can obtain one equation that is of the fourth order in omega, and then from this equation, here in this example we included also the numbers to make it a little bit easier to understand. But then once we have the equation, we can plug the numbers, since this is the equation of fourth order in omega, and then the two solutions, the four solutions actually, will be the square of the frequency. So you take the square root and you find the natural frequencies. And then you use natural frequencies to find your vector u1 and u2. Well, I would say, if we talk about the term J, so when we look at the linear system, we have the mass of the body, which is, from a physical point of view, when you have a body that is translating, the mass is responsible of the inertia of that body, right, going back and forth. When you look at a rotating object, instead of having the mass, you have the moment of inertia, which is indicated with the letter J. So from a physical point of view, these two problems are actually very, very similar. It's just that in one case we have translation, so we have all the terms that are related to translation, which means like a linear displacement and linear acceleration and mass. In the other case, for the two disks, we have all the terms that are related to rotational motion, which means we have rotation, so theta, rotational acceleration, and instead of the mass we have the moment of inertia, because that is responsible of of the rotation. So the term J is basically the physical equivalent of this term M here, and actually that term J shows up in the mass matrix. We still call it mass matrix even if there is no mass, but we have moment of inertia. Make sense? I'm going through the note. Why you think about other questions, I'm going through my notes to try to suggest things that should be reviewed before the midterm. Okay, well, we started with single degree of freedom. We looked at simple harmonic oscillator and the equation for simple harmonic oscillator. We determined what type of equation is this. We looked at a solution of that, and then we found the particular solution, the general solution first, then we applied move these things around. Then we looked at the initial conditions to try to find the particular solution, and then we found a particular solution that includes the natural frequency, which depends on K and M, and then the initial conditions of displacement and velocity. Then we draw the qualitative response, which is basically a wave with constant amplitude because we don't have any damping in this case, and then we defined a few quantities: the period, 2 pi over omega n, the frequency expressed in hertz, and the frequency expressed in radians. Remember, the best way to distinguish these two is to just look at the units. Some textbook will call this one natural frequency, some other textbook will call this natural frequency. So to avoid confusion, just look at the units and you know which one we are talking about. Then, okay, then there was I think it was an example. So we look at the maximum amplitude. Then we look at the pendulum, which from a mathematical point of view is basically identical, because we obtain the equation that has the exact same form, but of course instead of looking at linear quantities, we look at rotational quantities, so theta and theta double dot. And here was the comparison between the pendulum and the spring mass, which means that if mathematically they are described by the exact same equation, it means that they have the exact same solution. So mathematically this one and this one are perfectly identical, we just change the symbols. Then we look at a couple of problems for the pendulum, and then we introduce the damping. So when we introduce the damping, our equation changes slightly because we have this extra term here, Cx dot. So the dashpot also applies a certain force on the mass, which depends on the velocity of the body. And then what did we do? So this is okay, this is the relation between the different forms of the solution. Then for damped systems we looked at the characteristic equation. From the characteristic equation we can solve, and then we can find lambda 1 and 2. from this one we can determine if the system is under, then we can introduce the concept, the parameter zeta, which is the damping ratio, and then by looking at zeta, in order to make basically all the quantities positive, we have that the system can be underdamped if zeta is between 0 and 1. It could be overdamped if zeta is greater than 1, or it can be critically damped if zeta is equal to 1. In these two cases, we have non-oscillatory motion. In this case, we have an oscillatory motion. Instead of having constant amplitude, the amplitude decreases in time. And basically, when we look at this function here, this plot, this wave with decreasing amplitude, it's basically nothing but a combination between this function here, which is the exponential function, and this function here, which is the sinusoidal function. So by combining these two, you obtain a sine wave that has decreasing amplitude. And then okay, for this case, for the case of underdamped motion, so when we have oscillatory motion, which is the one that is of interest for vibrations, we can look at the particular solution. So the particular solution means that we are looking at the initial conditions. So the displacement at t equal to 0, the velocity at t equal to 0, and then by solving basically this system of two equations, we can find the amplitude and the phase. What else? Okay, then we looked at examples, problem 1, problem 2. Okay, then we talked about springs in series and parallel. So when we have spring in series, it means they are subjected to the same force, and we can find the K equivalent in this way. When we have springs in parallel, doesn't mean that they have to be on the same side. They can also be on opposite sides, like in this case here. What characterizes springs in parallel is that they are subjected to the same displacement. They are stretched or compressed by the same amount. And here is how we find the K equivalent. We went through a problem with a bunch of springs. Then we talked about materials. This is the stress-strain diagram for a certain material. Could be metal, plastic, and then we can distinguish between elastic behavior and plastic behavior. So while I go through this, if you have questions, you can interrupt me, and then we can talk a little bit. But I'm just going through all the topics that we covered during the semester. So here we talked about materials. So again, stress-strain diagram. We can distinguish two types of behavior: elastic behavior and plastic behavior. Elastic behavior means that the deformation is temporary, which means that if we apply a certain force, that will bring a certain stress up to, let's say, this point here, so up to this limit, and then we remove the force that we are applying, the material will go back to the initial condition like nothing happened. If we apply a value of the force which brings a stress that is higher than this limit, and then we remove the force, we remove the external force, some part of the deformation will remain on the material. So that is called plastic deformation. Now, why we did this one? Because if we focus on the elastic portion, basically materials behave exactly like springs, because we have a linear relationship between, in this case, stress and strain, which is equivalent to the linear relationship between force and displacement for the springs. So if we have beams made out of certain materials, we can compare them to spring, we can model them as springs. So if we have axial deformation, we have the K equivalent that depends on EA, which is the axial stiffness. If we have a twisting motion, we also have a K equivalent for this rod, which is GJ over L, where GJ is the torsional stiffness. And then we have transverse motion, where we also have a K equivalent, where the K equivalent is 3EI over L cube. So here we have EI, which is the flexural stiffness. And then we looked at the case of the helical spring, where we can design a spring. If we want to obtain a certain stiffness of the spring, we can decide the type of material. For the wire of the spring, we can decide the diameter of the wire of the spring, we can decide the radius of each turn, we can decide the number of turns. So by changing all these parameters, we are going to change the stiffness of the spring. So we can design the spring to obtain a certain value of stiffness. Then a couple of problems about materials, and then here we talk about logarithmic decrement. So logarithmic decrement is a concept that we use if we want to determine the properties of a certain structure starting from its behavior. Because up to this point we looked at the behavior from the properties, which means we looked at the response, so x of t, by knowing what type of stiffness we have, by knowing what type of damping we have. But in this case we do the opposite, because we look at the graph. So this is valid for underdamped systems, remember. So we look at the graph, we measure the amplitude at 2 points. From the amplitude at 2 points, we can apply this first equation, so we can find this delta, which is the logarithmic decrement. And then from delta, we can find the damping ratio, because the damping ratio is related to the logarithmic decrement by this relation here. So we do the opposite. This is what is done in experimental practice, basically. Problem here. And then we talked about the energy method. So we can also find the equation of motion by using the energy method. Energy method means that we look at the potential energy, kinetic energy. We know that if a system is conservative, the summation of potential and kinetic energy is constant. We can express the kinetic energy as a function of the velocity of our object, of our mass. The potential energy is given by gravitational potential energy and elastic potential energy, so gravitational and elastic. Gravitational depends also on the displacement, elastic depends also on the displacement, and then once we have the kinetic and potential energy, we can plug them here, v plus t equal to constant, and then we can calculate the first derivative. When we calculate the first derivative, the velocity becomes acceleration, the displacement becomes velocity, and then we can and the constant becomes 0, so we can simplify, and then we obtain the equation of motion for of course, identical system, no matter which method we use, we must obtain the exact same equation. Then we did the same for the pendulum. In this case, we look at the potential gravitational energy here. We look at the kinetic energy, and then we do the same thing. V plus t equal to, t plus v equal to constant. We derive, which means equal to 0, simplify, and then we obtain our equation of motion for the pendulum. I think this was a problem that we went through. Okay, and we also use the method of energy to calculate directly the frequency, the natural frequency. And to calculate the natural frequency, we applied this concept here, that since the summation of kinetic and potential energy is constant, it means that if one goes up, the other one must go down, right? This is exactly what happens when we have the mass that goes up and down with the with the spring. When we have an increase of potential energy, we must have a decrease of kinetic energy, which means that over the entire cycle, the maximum potential energy that we can have must be the same of the maximum kinetic energy that we can have, because it means that if one is maximum, the other one is 0. So from this concept, we can write this equation, U max equal to T max, and then we can determine the spring displacement, and then we find the max displacement. The maximum velocity is a omega n, like we saw in a previous example, and then by equating these two quantities, we can find the natural frequency, exactly like we did with the other method. This was an example of finding natural frequency, but with a rotation of this object. We actually have rotation and translation for this one, so we need to keep into account both contributions for the kinetic energy. This was another problem with the method of energy. Here we talked about instability. So up to this point, we always had k over n, or the natural frequency, always positive, but that's not always the case. Or at least we need to see how we can express the natural frequency, and depending on the relation between these quantities k, l, m, and g, this term can be either positive or negative. If it is positive or negative, of course we talk about a system that is stable or unstable. This, I think, was the review before the first midterm. Yes. Review of the first midterm. And then we talked about forced systems. So forced system means that we can have an external force. Of course, the external force must be a function of time. We looked at this first case where the external force is like a sine wave, and we can include as a cosine of omega t. When we write the equilibrium equation, of course we have to include that external force, and then this is the new form of the equilibrium equation, which can be written in standard form as well. And then we looked at all the steps to find the solution. So the solution is a summation of homogeneous and particular, and then we can go through all the steps to find the particular solution first, and then once we find the particular solution, which is basically this portion here, then we can find the total solution by applying the initial conditions. Here was the example problem, and here are all the steps. Then, of course, we expanded for forced and damped. This process was a little bit long, so we needed to cut it down to basically skip some step, but the process is always the same. We look at the equation of motion, we look at the general solution, then we look at the total solution, then we look at the particular solution, and then we said that we can divide the total solution in two portions. One is the transient solution, the other one is the steady state solution. And we said that we need to focus on the transient or the steady state depending on two factors. One is the timeline that we are looking at, and the other one is the damping coefficient. If the damping coefficient is big enough, we can ignore the transient, otherwise we have to consider that. And in general, if our timeline is long enough, we can also ignore the transient and focus on the steady state. This was another problem, another example we did. And then we talked about the base excitation, which was a kind of introduction to 2 degree of freedom systems, because here we have the base, the mass, connected to each other through the spring and the dashpot. So we will have a certain function for the input, so for the base motion, we can calculate the velocity, and then we can draw the free body diagram and look at all the forces that are applied on our body. And then we move to the 2 degree of freedom system. We already talked a little bit about this, the steps that we have to follow to solve this problem. We find the natural frequencies, and then we find the vectors u1 and u2 here, and then once we find the vector u1 and u2, we can plug them in the solution, and then we can find finally a1 and a2, and then once we find a1 and a2, we can finally have the final solution, so the x1 of t and x2 of t. Okay, here we have another example. Then we looked at the modal analysis. We said that the main purpose of the modal analysis is to basically split all the degrees of freedom, because through the modal analysis we can obtain one equation for every degree of freedom in our system. So by decoupling the system, it will become much easier to solve the equations, and this is basically the main reason why we use modal analysis. It may seem longer, and probably is longer, but it's actually easier. There are only mathematical steps that need to be followed. Now, of course, if you have a 2 degree of freedom system, it can be not much of a difference to use the modal analysis versus the classical method. But when systems become bigger with 3, 4, 5 more degrees of freedom, solving a system that has 5, 6, 10 differential equations that are all coupled becomes impossible. So in that case, we need the modal analysis to decouple all the equations, so we go back to the problem of 1 degree of freedom systems. And here we have the steps. Also on Canvas you can find the notes that I wrote for all the steps that need to be followed. And then the last thing that we looked at is the concept of continuous systems. We looked at the differences between the discrete and continuous systems. The main difference is that for discrete systems we only have time as a variable. For continuous system we have time and space. And then in this case we have a finite number of degrees of freedom. In this case we have an infinite number of degrees of freedom. The type of equations that we use to describe the systems are ordinary differential equation for discrete system or partial differential equations for continuous systems. And then the way how we solve, of course, is different because we have different equations. We looked at the wave. equation, we saw that we can find this in different situations. So for acoustic, optics, and in fluid dynamics as well. So here we saw basically all the assumptions that we need to make to solve, to find the equation of motion. We have a certain tension on both sides. We need to introduce the linear density, and then of course we talk about the acceleration, and then finally we can write our Newton equation for summation of forces equal to m times a, and then we have the summation of the forces. Here is the acceleration times the mass when we introduce the linear density, and then with all the steps eventually we can come up with this form of the equation of motion for a vibrating string, where this term here, t over rho, is actually the wave speed. Could be the speed of sound if we talk about sound waves, it could be the speed of light if we talk about light wave, and so on. And then here we saw the way that we can use to solve actually the wave equation, which means that we use a separation of variables. So the solution can be given by the product between two functions. One is only function of x, the other one is only function of t. When we derive this with respect to time and with respect to space, we can plug back and we can say that these two must be equal to a certain constant, and which means that we come up with two equations, one only in space, one only in time. So we can solve these two equations by looking at the and then we have to look at the boundary and initial conditions. We have infinite solutions for this one, which means that we have a different solution for each value of n, 1, 2, 3, 4. They go up to infinite actually. So the system is continuous, which means that we have infinite modes of vibration. And then we introduce the beam, which is and then we look at the transverse vibration of the beam. Even in this case we looked at the equilibrium of the small portion. In this case the internal forces are internal bending moments and internal shear forces. Of course we have some motion, so we have the inertia component, and then from this free body diagram we can write the equilibrium in the vertical direction, the rotational equilibrium, and then we need to recall a little bit the concepts that we covered in previous classes, basically the relation between shear force and bending moment. And then with this one we can write the final form of the equation for a vibrating beam in transverse vibrations. And then we said in this case we have a fourth order, because here we have the fourth derivative of the deflection with respect to x, which means, and then we have also the second derivative of the deflection with respect to time, which means that we need 6 conditions, 2 in time and 4 in space. For the conditions in time, we can, for the condition in space, we can look at the boundary conditions. So, and these boundary conditions depend on what type of constraints we have for the beam. So we saw the example of fixed, where we don't have rotation, we don't have displacement at the two ends, or fixed and pinned, when here we don't have rotation and translation, and here we don't have translation and moment. So mathematically, of course, we have to write these conditions. And this was the last thing that we saw last time. And actually going through all these things that we saw, I've been thinking at other questions that I can include that in the meet. Any question? We still have few minutes. So if you have other questions, we can spend a few more minutes. If not, we are not going to meet next Monday because it will be the time of the midterm. So as I mentioned before, you will find it on Canvas starting at 7:30, and then it will close at 8:50, and then we will meet again next Wednesday when we will start with the presentations, which I think are due today. Is it today? I don't know. Yes, they are due today. I didn't check submissions, but if you didn't submit your presentation yet, please submit by the end of the day today. And of course, it's going to be one presentation per group, so you need only one per group. Yeah. So if you look at the assignment, you will find the Excel file. The Excel file has two tabs. The first one is with the rubric, the second one is with the order of the presentations. So if you go there, you can find it. Sure. Yeah. Text box. Let me check. Just give me a second so I can open Canvas. Evaluations, assignments, project presentation file. Oh, okay. File uploads. Okay, so I just update. Thank you very much for. Okay, I see that some already submitted, but submitted what? Because if it was just text. Okay, someone put some link. Okay. Okay, now it is updated. So I see that one group already submitted basically a link. So if you can please resubmit with the actual file, that would be appreciated. But thank you very much for pointing this out. I updated, so it should be fine now. Please check if you have a minute now, so and let me know if you can see the new the new format. Also, I didn't put any limitation on the type of file that you can submit, but as I mentioned last time, I would suggest to submit like a PDF, or if you submit like a PowerPoint file, I would say try to avoid animations that are not like strictly necessary, like text entry, transitions, fancy transitions between slides and things like that. Makes sense? Any other question? I see. Okay, if you I guess the GIF is the animation of the structure that is showing the modes, right? Something like that, right? Okay, if that's the case, I think that's okay. So once we move to that slide, then the animation will keep going and there is nothing else to do, right? I'm saying I would avoid like the entry of an image or the entry of a text box, things like that. But if you have one new slide and the slide has the GIF with the that shows the vibration of the structure, that's okay, that's fine. So you can submit the PowerPoint in that case. I think it would be better if you submit as a PowerPoint. So if you download, and yeah, because I will open all of them in PowerPoint and then just show this, or PDF if it is in PDF. All right. Sure. Other questions? All right. Oh, okay. Well, the report was already submitted. Okay, yeah, I made the mistake of not making it as a group assignment. So I saw that basically almost everybody submitted, which is fine. So when the grading will be done, we will simply give the same grade to manually give the same grade to all the students of the. So if someone in your group submitted the project, that's okay. That will be graded, and you will get the same grade of the other components of your group. Yeah. That's okay. That's okay. It's fine. Other questions? Alright, if there are no other questions, I will give you back 5 minutes of your life for today. And if you have questions, please send me an email and I will try to reply as soon as I can.